All right, so we'll go ahead and get into this next section of notes for honors geometry here. This is going to be 8.1, and we were talking about similar figures. And before we do that as well, if you have not already, you can go ahead and label the next unit in your notebook here. And Unit 8, this is going to be a shorter one. We're not going to have a test with this. We'll just go have a quiz. And this is going to be talking about similarity. So you can label this in your notebook, Unit 8, similarity. And then specifically today, we're just talking about similar figures. Okay, date that we're going to do this is the 2nd. And the objective for today is we want to be able to find measures and variables using these ideas that we talk about with similar polygons. Okay, so what does that mean if we're talking about similar polygons? Well, similar polygons are, I could say let's say two polygons that have the same shape but different size. Okay, have the same shape but different size. So no pun intended, but this is similar to what we talked about with congruent shapes. When we talked about congruence, we said these two shapes that I'm looking at, for instance, these two triangles are the exact same. Here we have the same kind of idea, except we're just going to say they're different sizes. So one is just going to be much larger or much smaller than the other. So for example here, if I look at this simple one, let's just draw a couple triangles here. And let's keep it simple. Let's say these are side lengths of 8, 8, and let's say 6 here. Okay, so this would be one triangle, right? We have some different side lengths here. All it's saying when I have similar polygons is it's the same kind of idea except a different size. So for instance, we could say this one is 4, this side length is 4, and this side length is 3. Okay, this would be an example of similar polygons here. Just being able to look at them, they look the exact same. They're both isosceles triangles, but their side lengths are obviously different from each other. Okay, so if this is the case, we have some different properties that we want to make sure we can pay attention to so that we can use that to solve some different problems. I'm going to say if two polygons are similar, then we know two things. Okay, first thing about the side lengths is we're going to say the side lengths are what we call proportional. And I'll explain more of what that means here. And you can kind of see that when you look at that example that we just wrote. They have the same proportion, or in other words, the same relation to each other. One's that much bigger than the other. Okay, and like I said, we'll have many problems in practice with this here in a bit. Okay, so the side lengths are proportional, and then for the angles, because that's the other part of the shape, okay, the angles are actually all going to be the same. Will be the same, or congruent to, I'll say, keep it more mathematical terms, will be congruent to each other. So that part's not going to change from what we talked about with congruent shapes. All of the corresponding angles are still congruent. The only thing that's changing is just the lengths of the sides. Okay, and then one other thing we need to talk about as well, a similarity statement. We saw this kind of idea when we talked about a congruent statement. Similarity statement is the same kind of thing. It tells which points are corresponding. Tells us which points are corresponding. Because just like before, it's important that we know which points are supposed to match up with each other. And sometimes that's not always easy to do if I'm looking at two different shapes. So for example here, an example of a similarity statement is I would say triangle, for instance, ABC. And we're going to say is similar to. And so basically all that is that symbol right there. We're getting rid of the equal sign and we're basically just keeping the squiggly symbol. And I'm going to say that's similar to triangle DEF. Okay, so that's all I have for similarity is just this basic idea. The points are going to match up. You can see that A is supposed to correspond to D, B to E, and so on and so forth. And then you can also see, or you now know that the sides are going to be proportional and the angles will be congruent to each other. Okay, so for example, let's put this to use here and talk about more about what this means when I mention proportional to each other. So if you'd like to, you can pause your video and sketch this diagram here. And we're saying we have these two triangles, and we're saying FGH is similar to triangle JKL. Okay, and it's good that this is written out for us because now we know which points are supposed to line up with each other. Okay, and saying if this if this is the case, we want to use the similarity statement to give properties about angles and side lengths here. So let's start with angles, because that part is going to be a little bit easier. Angles here. And it's asking, what do I know about some of the angles? Well, remember, if the shapes are similar, then all the angles, or at least the corresponding angles, are going to be the same. So for example, if I'm looking at angle F here, I can look either at my diagram, or I can just look at the statement at the top and see which angle should that line up with. That should line up with J. So now I know that angle F is going to be congruent to angle J. That part is very similar to what we've seen with congruence here. Okay, we can continue to go around. Next one here, we have angle G. And again, I don't even need to look at the diagram. I can just see up here, angle G is supposed to correspond with K, so angle G is going to be congruent to angle K. And then same thing with the last pair of angles as well. I'll go to there. Angle H and angle L are going to be congruent. So not too much difference in that aspect. Angles are still congruent to each other. Simple enough. Okay, now with the sides, it's not saying that they're congruent to each other. It's saying that they are proportional. And so what that means when I say proportion, it's basically kind of similar to setting up a ratio. It's saying, how are they related to one another? In other words, how much bigger is one side than the other? So let's start with the first side here, FG. If I look at this, FG is supposed to line up with JK. And so what I can say here, if I'm going to set up a proportion, I just need to set up a fraction. So what that means is I can say FG over JK. Okay, this would be an example of a proportion here, setting one over the other. And it doesn't matter which one's on the top or which one's on the bottom for this first part, as long as you just have this fraction set up. And since I'm going to say they're all proportional to each other, I'm going to say that's equals the same thing as if I do this with other pairs of sides. So let's take our next pair of sides here, GH, and we know that should line up with KL if we're looking at how those letters are written. So now, since FG was on top, on the next proportion, I'm going to have GH on top, and that's going to be over the other side that is corresponding to KL. So this is what a proportion is, or this is what it means. Is it saying the same difference between FG and JK in terms of how much bigger one is to the other? That's the same kind of separation as GH and KL, okay, which is also the same thing as the last pair of sides here. So if I look, FH and JL would be my last two sides. So I'm going to say FH, or it's going to be equal to FH over JL. Okay, this is what we're talking about when we say proportional. And we're going to set up a lot of proportions and problems like this to be able to solve for different lengths and variables. Okay, and then notice we don't need to do a final statement or a similarity statement because we've already been told that they are similar from the beginning. Okay. One other term that we're going to make sure we want to know as we go into problems like this is what we call a scale factor. Okay, so a scale factor is just the proportion of side lengths, proportion of the side lengths from one similar shape to the other. And usually you go bigger to smaller. Okay, so for example here, let's take that, or let's draw a different example here. Let's say we'll draw some rectangles. Again, trying to keep it simple. Let's say these have side lengths of 2 and 2, and keep it, we'll go 4 and 4 here. Okay, and then for this rectangle, let's say we have 1 and 1 and 2 and 2. So I'm just choosing these side lengths. Doesn't really matter what they are. Okay, the scale factor here, if I'm going to name these here, let's say A, B, C, D, and E, F, G, H. Scale factor is going to go in the order that it's written. So if I ask for the scale factor from A, B, C, D to E, F, G, H, it means I'm going to write the side length for A, B, C, D first, and then E, F, G, H for the second one. So we can choose side lengths here. It doesn't matter which ones we choose. So for example, let's choose AB, side length of 4, and I'm going to put this in a proportion, or in other words, I'm going to put this in a fraction here. And we'd say AB is supposed to correspond to what in the other rectangle? Well, that would correspond to EF, or in other words, 2. So the scale factor here from ABCD to EFGH is 4 over 2, which, simple enough, just equals, if I simplify it, 2. Okay, so in other words, what it's saying, as you can kind of see just by looking at it, is all the lengths in this shape are going to be twice as big as all the lengths in this shape. Okay, and that same scale factor is going to apply to any other sides that we look at. So 2 and 1 example would also have a scale factor of 2. Okay, this is what it means for them to be proportional. So I'm looking at how much bigger is one than the other. Well, the rectangle on the left is twice as big, or 2 times as big as the rectangle on the right. Okay, and that's how we're going to use it. Okay, so putting that to use here, being able to solve for different variables. Again, you can take a sec and sketch this diagram for me. And in this case, just like before, we're told ACDF is similar to VWYZ. And we want to use that to find X and find Y. So if I'm looking at X here, and really it says I want to use the scale factor as well, so we'll do that in a sec. If I'm looking at X here, I only see one side length with X in it, and it's just this one FD at the bottom here. How am I going to use this where it says I want to use the scale factor? And so what I need is I need to set up a proportion just using 2 of the sides that I already know. So if I'm looking at the other sides in this shape here, I notice with AF, that is 12, and that should line up with VZ and the other side, in the other shape here. So 3y minus 1. Well, the problem is I can't set up a proportion with these two yet because one of them, is an actual number, but one of them has variables in it. So I'm looking for 2 sides where I know that they're going to just be whole numbers, because then I can figure out how much one is bigger than the other. So we can look at our other side here. If I look at the side length of 9, that's CD, and I see if I look at my letters up here, that should line up with WY. Okay, and this is why I check my letters at the top, because it might look like this is just a shape that's being reflected, but actually it's kind of being rotated. So the sides that you think might line up might not be the case. That's why we look at the letters. Okay, so I see this here. So my scale factor is going to be 9 over 6, because I take the side length from the top shape and the side length from the bottom shape. So I'm going to say 9 over 6, and that's going to be equal to, and now I can use this scale factor to plug in my variable that I'm trying to find. So X is on the top shape, so I'm going to put this on the top. And then on the bottom, the line that matches up with that would be 10, because I see DF up here should line up with YZ. Okay, so this is my proportion now. 9 over 6 is going to equal X over 10. And there's a few different ways that we can solve this. The one that we're going to use mostly is just what we call cross multiplication. So what I can do to solve this is I can say that whenever I multiply these two, or cross multiply, that is always going to be the same as when I multiply these two here. So for instance, if I wanted to make a statement from this, what I can say is 6 times X is always going to equal 9 times 10. And that is always the case when you're dealing with proportions. You can just cross multiply and set those two products equal to each other. So 6 times X, simple enough, is just 6X, and then 9 times 10 is 90. And now we can just go ahead and solve this for X like a normal algebra problem. So I would divide by 6 on both sides, and I'd get X equals 90 divided by 6, which is 15 here. Okay, and this would be my final answer. If I wanted to, I could plug this back in and make sure that is correct, and it would be. Both of these fractions would end up simplifying down to 3 over 2. Okay, so that's X, and then we're going to do the same thing with Y. So we're going to use our scale factor again, 2 side lengths that I know, 9 over 6, and this time I just need to find the side lengths with Y. So I see I have that expression 3y minus 1 right here, and I notice that's on the bottom shape, so I'm going to put that on the bottom as well, just like I did with 6. And then up top, the side that corresponds to that would be 12. Okay, and again, this is why we use cross multiplication, because now it's a little bit simpler to just set this all up. So I'm just going to cross multiply here, and what we can say is we can say 6 times 12 is going to equal the same thing as 9 times 3y minus 1. And since this is an entire expression, I'm actually going to put this in parentheses as well. Okay, so now we just need to simplify. So 6 times 12, I can figure that out. That's 72. And then if I have 9 times 3y minus 1, remember, this is why I put the parentheses. So now I know I need to distribute. I can't just multiply that 9 by one of the terms. I need to multiply it by both. So 9 times 3y is 27y, and then 9 times negative 1 is negative 9 here. Okay, so I need to make sure to multiply it by both, and now we can solve. So I have a negative 9, I can add that to both sides. When I do that, those cancel. I have 72 plus 9, that's 81, equals 27y. And then last step here, divide by 27. And I'll just bring this answer over to the side because we're running out of room. And I get 81 divided by 27. We could type that into our calculator if we didn't know, but that's going to be 3. So y equals 3 here. And just as always, I can always plug that back in if I'm not sure or want to double check that. Okay, but this is the idea. These are the kinds of problems that we're going to be doing. A lot of proportions and then a lot of cross multiplying to solve. Okay. One other idea, or one other property that we have with similar figures is we actually know information about the perimeters. So remember, perimeters is when you add up all the sides on the outside. And since all the sides are proportional to each other, what I can say is the perimeters of similar figures will always be, or will always, let's say, will always have the same proportion as the scale factor. Okay, we'll have the same proportion as the scale factor. So in other words, all the proportions or the fractions that we look at with the side lengths, those can also apply to just the perimeters as a whole. Okay, so last one here, example 3, practicing this a little bit. Again, you can take a sec and sketch this diagram if you'd like to. Okay, and we're going to use these similar figures to find the perimeter of the top shape, RQPTS. And we are told they are similar. Okay, so notice here, if I'm looking at these shapes, before I even get started on working through how I would solve this problem, notice we can actually find one of the other side lengths in the top shape. I know PT is also going to be 3 because RS and PT both have 4 dash marks. Now RQ and QP, I know that they're the same, but I don't know exactly what they are. And so this is why we have to use the scale factor, and it's why we can't just add up the sides of that shape because I don't know all the sides of that shape. So if I look here and I'm trying to find my scale factor, again, I can go ahead and label these sides in. I know this is 8 because those both have 1 dash mark. And I know this is 4 because they both have 2 dash marks. And I can set up a proportion with this in mind here. To do that, I need to find the scale factor, and I need to find 2 side lengths that are both numbers. Well, if I notice here, I see I have side lengths here that are corresponding that are 3 and 4. And so I can set up a proportion here. So my scale factor from the top to the bottom is going to be 3 over 4. Okay, and what that definition just said that we wrote down is we said that's going to be the same proportion as the perimeter from one to the next. So in other words, 3 over 4 is the same thing as the perimeter of our top shape, RQPTS, over the perimeter of the bottom shape. In this case, ABCDE. Okay, this is what that definition is saying. The scale factor, 3 over 4, is the same thing or the same proportion as the perimeters. Okay, well this is good because I can actually find the perimeter of the bottom shape here because I have all the sides. If I take 8, 8, 4, 4, and 6, I can just add those all together here. Whoops, plus 4, plus 6, plus 6 here. And this is going to end up giving me 30. So now my equation can say this, if I move this to the side here, is I'm going to say 3 over 4 is the same thing as, okay, perimeter of RQPTS, we don't know, so I'll just call that X for now. And the perimeter of the bottom shape, we do know, we just found that to be 30. Let me double check there, 16, 22, 30, yeah. Okay, so now that we have this here, same kind of thing as before. If I want to solve, I can just cross multiply. So I can multiply these two, multiply these two. And what cross multiplication tells me is that 4 times x is going to be the same thing as 3 times 30. Okay, and now we can just go and simplify. 4x equals 3 times 30, which is 90. And then our last step here, we're just going to divide by 4. And I get x equals 90 divided by 4. And I can type this into my calculator if I want. 90 divided by 2 is 45, so divided by 2 again, or if I cut that in half again, that's going to give me 22.5. Okay, and in this case, we do end up getting a decimal. We can double check and make sure that we did our work correctly, and it looks like we did. Okay, so our final answer here is x equals 22.5, or in other words, the perimeter of RQPTS is going to be 22.5. Okay. Okay, so just noticing that we can use all these different ideas with the side lengths and then with the perimeters as a whole. Okay, as always, if you guys have any questions with any of this, feel free to let me know. But otherwise, our assignment for today is going to be 8.1 homework, similar figures. All right, thanks, guys.